So welcome to homework assignment number 3. This is all about particle filters. I'll ask you 3 questions, and then we have a fairly involved programming assignment. So here's my first question. Consider the following world with 4 states, A, B, C, and D. Suppose we wish to initialize our estimate with uniformly drawn particles. My question is, what is the probability that cell A is empty? And I'm asking this for different values of n. N equals 1, 4, and 10. For n equals 1, it's 0.75, with 3/4 chance the particles will find themselves in B, D, or C. And there's only a 1/4 chance that the particle is in A. For n equals 4, it's 0.316, which is the same as 0.75 to the 4th. For each particle, we have a 75% chance to be outside A. 0.75 to the 4th are the chances all 4 particles are outside A. And as we move on, we get 0.75 to the 10th with a 0.0563. Question 2. Consider the same world as before with 4 states. And now we're facing a situation in which there's 5 particles in A, 3 in B, 3 in C, and 1 in D. We will now take a motion step. So this is not about measurements, just motion. Our robot moves with 50% probability horizontally. So for example, if it was in D, it would move to C. It moves with 50% chance vertically, but never diagonally, and it never stays in the same cell. After one motion step, how many particles do we expect in cell A, B, C, and D? Answer the same for the asymptote. So if we move infinitely often, what is the distribution that we expect this to converge to? So I somewhat sloppily wrote after infinite steps. This is really what does it converge to in the end. The correct answer after one step is 3, 3, 3, and 3. So for example, for cell A, we can only get particles from B or C. Those will come to A with 50% chance each. So 6 times 0.5 is 3 for A. Each cell has exactly 6 particles in its total neighbors. So therefore, each of those cells gets a 3. Asymptotically, this won't change. So it's again 3, 3, 3, 3. And I apologize, it is a little bit misleading here that all these answers are the same number. But that's what this example gives us. In question 3, I'd like to quiz your intuition. Suppose we run a particle filter with n equals 1 particle. What will happen? It'll work just fine, perhaps with a slightly larger error. It ignores robot measurements. It ignores robot motion. It likely fails, or none of the above. You can check multiple boxes on the left. The correct answers are it ignores measurements and will likely fail. It ignores measurements because the measurement sets the weighting factor in this resampling process, but with only 1 particle, the same particle will be resampled no matter what. So the chances of the particle to be resampled is 1, therefore it's independent of the actual measurement, and the robot truly ignores the measurements. Because it ignores the measurements, it'll likely fail, so works fine is incorrect. And for ignoring robot motion, that's not the case. Even a single particle can be sampled forward. So these are the 2 correct answers over here. So here's our programming assignment. In class, you already programmed a particle filter for a really simplistic robot that was able to measure ranges to landmarks and moved pretty much like a trash bin. Now I'd like to replace it with a more interesting robot that is more realistic. In particular, I'd like you to use a car. So here's a car. A car tends to have 2 fixed tires and 2 steerable tires in the front. Suppose the location of our car in a coordinate system is given by its x-coordinate and its y-coordinate, and I'm picking the halfway point on the rear axle as the reference point, and by its heading direction, theta. So the state will be x, y, and the orientation theta. Then this car also has a steering angle, it's called the alpha. The question is, how is the state affected by driving a certain distance d with a fixed steering angle, assuming the initial state is x, y, and theta? It turns out to answer this, I also need to know the length of the vehicle, which I will just call L for length. That is a constant throughout our consideration. This is usually called a bicycle model. Obviously, it suffices to look at one pair of tires, because the other one, at least in approximation, runs pretty much parallel. So if we look at the robot locally, where we have a steering angle alpha, robot length L, and we're driving the rear tire forward by distance d, then the robot will turn to the left. And its turning angle, beta, is proportional to the distance that the rear tire moves forward, divided by the length of the vehicle, times the tangents of the steering angle. To now compute the changes of x, y, and theta in the local coordinate system, we realize the turning radius, r, of this robot is simply the distance that we drive forward divided by beta. So it's relatively simple math, which I don't want to explain in detail. This means that the robot is turning around a point over here, call it Cx and Cy, and after the turn, the vehicle is located somewhere over here. In global coordinates, here's the way we describe this. Cx is the x-coordinate of the robot x, minus, now we go to the left, the sine of the robot orientation before motion, times radius r. Similarly, Cy is this expression over here, y plus cosine of the orientation times r. And then after motion, we can go back from Cx to Cy to a new state over here, simply by adding in the turning radius beta. That is, our new x is Cx plus sine of theta plus beta times radius. And notice how this parallels this guy over here, except for two changes. What we previously subtracted, we're now adding, and we're adding beta to the argument of the sine. Same with y. And the orientation is just increased by beta, modulo 2 pi. Now this all works if the robot is actually turning. If the robot were to go straight, then r would become infinity by this division over here. So for small betas, in my code is smaller than 0.001, we can approximate this all as straight motion. Our new x is the old x times our driven distance pointed in the cosine of the heading direction. Similarly for y, we go in sine of heading direction. And the heading direction stays the same. You could add beta, which is basically 0, to be slightly more precise. Or you could just use theta. Doesn't really matter. So in this programming assignment, I'd like you to implement this piece of math over here in our particle filter. And to make sure you implemented it correctly, I will give you some example data that you can check. So now first part, I prepared a lot of software for you, basically copying the old particle filter software over and removing the motion and the measurement model for now. And in this case, I just want you to practice the motion model. So we assume a length of the robot of 20. We initialize the robot with this length parameter. And for this first iteration, we assume no steering noise and no distance noise. I set the robot to 0, 0, 0 in the beginning, and then I cache away a number of motions. And the way to read those is, this robot is moving by 10 in total with a steering angle of 0. Then it moves another 10 with a steering angle of pi divided by 6. And then it moves 20 again with a steering angle of 0. A pi over 6 is a left steering. So the robot should change its coordinates in the beginning just in the x direction because it's facing an x direction over here. Then turn left a little bit, go forward, and go straight again. Scrolling down a little bit, I also give you the code to run the robot. We've created it over here. We print the initial coordinate. And then for each of the motions in this list over here, we apply the myrobot equals myrobotMove command, and we print out the successor command. So if you get this right, this is the numbers I would like to see. Initially, the robot position is 0, 0, 0. That's just the one over here. It's our first print command. And then moves forward in x direction by 10. Orientation stays 0, so does y, because there's no steering. And now we steer. This affects x. It doesn't quite move 10. It only moves 9.86. In y direction, it moves 1.433, and its new orientation is 0.2886. And then we move straight again. And now the x-coordinate becomes 0.3903. Y-coordinate becomes 7.12. Orientation 0.28. So your code should output exactly the same values as over here. And just to give you a second test, so this is a sequence of 10 motions where the robot always moves 10 forward and always turns right by an angle of 0.2 in radians. And we look at the outputs, then we get the following array. You can see that the orientation starting at 0, which is the same as 2 pi, decreases all the way to 5.26. And you can also see the robot starts running in a circle. Whereas initially, we add almost 10 to the x direction, almost nothing to the y direction. As we come down here, we subtract quite a bit in y direction, because now the robot is going on a circle. So you should look at these numbers over here and see if your code matches these exact numbers that my code outputs. So here's a function move as a class function of the class robot that I implement where I get my motion vector, and the motion vector is defined to be steering first, then distance. I have a few error checks here to make sure that the steering angle doesn't exceed the max steering angle. The same is true for distance. I want it to be non-negative. And as I go down, I now implement the motion model. So let's just look a little bit more. I make a new robot copy as in my sample code in class. I copy all the generic parameters: length, bearing noise, steering noise, and distance noise. Nothing surprising here. Here I'll apply the noise, which you don't need it for the first implementation, but later on as we go on, you need it to actually add noise. So I'm just add Gaussian noise with the corresponding steering noise and distance noise parameters. If I set the mean of the Gaussian to be the steering command and the distance command, then this adds noise. I could have equally written steering plus random Gauss 0, comma, and then the noise parameter. And as I go down further, here's my execution of motion. My turning angle I called turn. This is the tangents of the noisy steering times the distance moved divided by the robot length. And as in my explanation of this question, I'm going to branch and see if my turn is significant enough. It's smaller than tolerance, and tolerance was set above to 0.001. Then I just model a straight motion. I get my new robot coordinates by the old robot coordinates moving in the orientation of the robot, cosine for x, sinus for y, and I increase my orientation by turn, which is likely essentially 0. In case I go beyond 0 or 2 pi, I do the modulo operation here just to make sure my angles are nicely between 0 and 2 pi. The more interesting case, as we go down in this program, you can see that I now calculate the radius as distance, the noisy distance divided by turning. Then I find the center of the circle around which I'm turning using the exact same math I just gave you. I now first change the orientation to be the new orientation by adding turn to the old orientation modulo 2 pi. And then I plug the new orientation into the sine and cosine argument, multiply by radius, add to the center of the circle to get my result. So this routine over here gives me exactly what I wanted. Now I want you to implement a measurement model using the function sense that is more characteristic of what's often used in the literature on robotics. Say we have a robot and we have a landmark, then the robot can measure the bearing or angle to this landmark relative to its own local coordinate system. So whereas before we measured ranges or distances, now we measure bearings or angles. We assume in the world there are 4 landmarks, L1, L2, L3, and L4. All of those are distinguishable. So the measurement vector is a set of 4 bearings that correspond to those 4 different landmarks. So when you implement this, I recommend you use the function a10(2), which is a generalization of aqueous tangents that takes as input a delta y and then a delta x. r10(2) would give you the orientation of a vector in global coordinates. You then have adjust for the fact that it's relative to the robot's local coordinates, which is done by subtracting the orientation of the robot. So this should give you the implementation of a bearing to a landmark. So for this implementation, I add a variable called bearing noise, which you probably already used because it was already referenced before. And I set it to 0, just so that we have no noise and you can check your code. We initialize the robot coordinates as 30 and 20. Motions are now irrelevant. But as I go down, I now just execute the following 2 lines of code. I print the robot coordinate as before, and I print the measurements. The robot is 30, 20, and the bearings to these landmarks will be 6.00, 3.72, 1.92, and 0.85. My question for you is, can you implement software that measures those bearings? If I change the initial orientation of the robot to be pi over 5, I now get my new robot coordinates over here, and my measurement vector outputs me very different values. And that's because this robot is now rotated, and therefore all the bearings to the landmarks do change. So it's 5.3, 3.1, 1.3, and 0.222. Implement a measurement function that gives me exactly those values. So here's my implementation of sense, the measurement model, as a function in the class robot. I produce a vector called z, which I return in the end, which have 4 bearings. And then I go through all my landmarks, and you already have the landmarks in your code. There's 4 of them. And I use the a10-2 function, which is the mathematical function for computing the angle. It takes the y value as the first argument, the x value as the second argument. So this is the local angle of a landmark relative to the robot coordinate. And because the robot has a global heading direction, I need to subtract this to get my bearing value. If I were to add noise, which is a flag over here, then I just produce a random noise adding variable. Definitely, this is something you shouldn't have implemented, but you need later as you implement the noise. And of course, I make sure that the bearing is normalized between 0 and 2 pi. I append it to the list and return it. So in our final programming exercise, I want you to put everything together and build a particle filter. And I'm supplying you with code that has as gaps pretty much the 2 functions you just programmed, move and sense. And some additional code that I copied from class, the particle filter code that you're familiar with, and also some code that helps you test your routines so you can make sure they're correct. The key new thing you have to do is you have to work on the noise. There's no bearing noise and steering noise and distance noise. The code that you wrote didn't have any of those. I want you now to modify your procedures to accommodate this noise, steering noise, distance noise, and bearing noise, and all of it should be Gaussian. So let's go all the way to the end. There's 2 test cases. This is the first test case, which are uncommented, so we can run it. And what this is, it creates a sequence of robot motions. Each of these time steps, the robot turns a little bit and moves forward. It also has 8 measurements, which are the bearings to those 4 different landmarks. And if I go up a little bit in the code, then you'll find that the ground truth final position was 93, 75, and 5.2. When I run it, it runs the routine particle filter with those motions and those measurements as an input, and it produces an estimate, which is 94, 71, and 5.2, which isn't exactly the same as up here, but it's close. So this is a particle filter working. I'm supplying quite a few functions for you. You should look around. One is called particle filters. That's exactly the same code we used in class and constructed together. I just copied it over. So if you look through this, you'll find hopefully no surprise here. And I'm also supplying you the measurement probability function, which is part of the implementation. So let's just go there. So here's the measurement probability function. There's something non-trivial here. I compute the predicted measurement, and then I compute a Gaussian that measures the distance between the measurements passed into the routine and the predicted measurements computed over here. That's all happening down here. Here's my Gaussian function with the exponential. And then I return my Gaussian error. There should be no surprise here. What's important is a little modification to the sense function that you haven't seen before. I can now give the sense function a parameter, and if I give it the parameter 0, it switches off the noise model. So you will need the noise model for forward simulation of the robot, but you don't need it for computing the probability of a measurement. So augment your sense function to have a flag that, if it's set to 0, switches on off the noise modeling and gets you the predicted best possible measurements. So what you have to do is, you have to find the part in the code that says only add modified code below here. You have to copy over your move function and then work in, as it says in the instructions, the steering noise and the distance noise. That is Gaussian noise. I hope you know how to do this. Then you also have to plug in the sense function, and you also have to plug in bearing noise and make sure there's a flag that allows you to switch off the bearing noise. And it should be an optional flag, so it should have a default value of the bearing noise being on, otherwise your code won't run. So here's how we will test your code. If you go to test case number 2, then I wrote a few extra functions for you that allow you to test your particle filters on many, many instances, just like the ones we'll be using for testing that are all randomly generated. Let me just go through that code line by line. Our test case will be 8 steps long. There's the same motions vector we had before of a slight turn on a circle. Generate ground truth gives us a sequence of measurements and a robot position that we can split as follows using a robot simulation. Then you run your particle filter over here, and the function check output down here compares the final robot position, the ground truth position, with your particle filter position, estimated position from here, and gives us a single flag whether this is all correct. So let me just do this. We generated a robot that finished at final location in this orientation over here. The particle filter came up with which is close to the originals, and my code check said true. Let me run it again. Different values, still true. Run it again. Different values, still true. Now it could happen that the code check says false. I just ran it 20 times, it said true for me every single time, but I've seen it say false. And the reason is it's a randomized algorithm, it's a particle filter. It might actually not have a particle at the right place. So when we test your routine, we're going to code our own code check output. We have our own function for this. But we're going to run it multiple times. And if you get it wrong once, that's not a big deal. So in summary, you will have to comment out all the test cases again. All you have to do is supply the missing function. You can test the correctness yourself. You can basically grade yourself with this test case over here. But when you submit it, have those commented out, because we have our own test software. And all we're going to test is whether your particle filter gives us a good estimate when we choose randomly the initial position of the robot, measurements, motions, and so on. So to implement the full particle filter, the only thing is really missing is the measurement prob function. And that's a little bit more involved because I have to really compare what the exact measurement would be for any robot particle and what I sensed, and compute the probability correspondence between the correct measurements and what I sensed over here. To do this, I calculate predicted measurements using the sense function. Here comes this little flag that I defined. If I set it to 0, then the sense function acts noise-free, which is what I want when computing the measurement model. But even if you left this out, you're going to get a fine answer, in my opinion. But that makes it a little bit more accurate. So that allows me to compute the exact bearings of the landmarks for my particle. And then I can compare these correct bearings, called predicted measurements, with the ones I received. And I do this down here in the compute errors routine, where I go through each measurement. And in 2 steps, I calculate the error in bearing. First, it's the absolute difference between my measurement that I observed minus the predicted measurement. And this difference might fall outside minus pi plus pi. So this line over here just brings it back to the smallest possible value in the cyclic space of 0 to 2 pi. So I'm adding pi, I do modulo 2 times pi, and then I subtract pi again. So this gives me a value between minus pi and plus pi. I then plug this error bearing into a Gaussian. And here's my Gaussian, where I square it, I divide it by my bearing noise squared, compute the exponential, and here's my normalizer that, strictly speaking, I don't really need for the implementation. I can safely omit it because weights are self-normalized. But I left it in, so it's actually really a Gaussian. And I take this Gaussian value and multiply it up into my error function. So for each of the measurements, I multiply in one Gaussian. And the final Gaussian is my importance weight that I return in this function over here. So this is not easy to implement. I hope you got it right. Scrolling further down in my code, I now implement the particle filter as follows. I use 1,000 particles, and this is exactly the same routine we had before when we generate our initial particles. Here I set the noise for these particles to be bearing noise, steering noise, and distance noise. I don't comment out the measurement generation step, I just take the input. And then as I go further down, I just run my particle filter. This is the exact same code you're familiar with. There's a motion update, there's a measurement update, and there's a resampling step over here. All those are the same as before. And in the very end, I just print the result of get position. So if I do this for my example, here's the position I get. And I guess I forgot to uncomment the robot coordinate over here, but if you look at the values over here, so this particle filter clearly does a pretty good job in estimating the robot position.